get started. So thanks everyone for joining us today. Welcome, this is our second seminar in our new ACEAS monthly seminar series. So before we start, just a reminder that if you have any nominations for future speakers in this seminar series, please send them along to either myself, Laurie Menviel, or Elisa Mantelli. Great, and so today we're hearing from Rishav Goyal. So Rishav recently completed his PhD at UNSW, working on Southern Hemisphere atmospheric dynamics. And this year has just started as an ACEAS postdoc, also based at UNSW, where he'll be working with Alex Sen-Gupta and others. And he'll be working on examining the interaction between atmospheric circulation and the ocean cryosphere system in the Southern Hemisphere. So if you want to share your screen, Rishav,
yep.
Get started. Thanks. Looks great.
Can you see my screen?
Yep, it's great.
All right. Wonderful, thanks. Thanks, Adele, for the introduction, and thanks everyone for joining. So I'm Rishav, and I recently started my postdoc. So I'll be talking about atmospheric circulation in the Southern Hemisphere extratropics. So the plan with this presentation is I want to introduce what the circulation looks like, what are the major features, and then talk about how it has changed and how it's going to change in the future. So in a nutshell, my presentation has three main parts. In the first part, which is a major part, I'll be talking about the major features and the dynamical mechanisms which create these features. In the second bit, I'll talk about how we understand the variability in these features. And then the final part will be changes that we have seen and that we expect to see in the future. So to introduce, Southern Hemisphere circulation looks like this. So it's strong, it has a strong zonal coherence. You see this strong westerly wind jet encircling Antarctica, which plays a major role in controlling the climate of this coupled atmosphere ocean sea ice system in the Southern Hemisphere extratropics. Okay. Yeah. So as I said, the circulation is strongly zonally symmetric, and this is what the leading mode of variability looks like. So if you look at the UF1 of mean sea level pressure, this is what it looks like. So you have this almost annular band of positive MSLP in the mid latitudes and a similar negative band of MSLP in the high latitudes. This in general we call as Southern annular mode. It has been previously called Antarctic oscillation, or some people also call it as a high latitude mode. Now, as you can see, this is basically a hemispheric scale pattern of climate variability. A similar pattern also exists in the Northern Hemisphere, which is called as a Northern annular mode. The major difference between these annular modes and other modes of variability that we know, like ENSO or IPO, is that these are purely atmospheric driven. So these are generated by the internal atmospheric dynamics in that extratropical region itself, whereas ENSO it's basically a coupled ocean atmosphere system. The time scale of variation is from weeks to years, so it has a long range of time scales on which it can impact. In other words, you can think of it like a red noise spectrum with an e-folding time scale of approximately 10 days. So that gives you a time scale of anything greater than 10 days is the time scale of SAM. And it explains almost 25 to 35% of total variance. So it has it's a major variability in MSLP, geopotential height, or wind fields, depending on which time scale you consider. Now, as I said, this is what the pattern looks like. But when we look at this pattern, we generally look at it in terms of zonal mean, or something like this. If you compare these two patterns, the first thing that you can observe is that zonal mean takes up most of this pattern, but there are still some features which can be very clearly seen, which are not represented by the zonal mean assumption. So if I have to divide the left-hand side pattern into major features, these are three major features that we divide the circulation by. The first is this zonally symmetric component, or more commonly known as SAM. The second one are these three high-pressure nodes, which is called as zonal wave number 3. And the third one is this Amundsen Sea Low, or more recently, people call it Amundsen Sea Low. And so that's the third feature. And over the last maybe 30 to 40 years, we have spent a lot of time understanding SAM, how it varies and how it impacts Southern Hemisphere, but we don't really know much about these asymmetric features. And that is what will be the major part of my presentation today. So the first feature is zonal wave number 3. So as I said, zonal wave number 3 basically means these 3 high pressure nodes. In this case, I have taken out zonal mean. So you see these 3 low pressure nodes in there. So wave number 3 basically means a sinusoidal wave, which has 3 highs and 3 lows. Now it's a quasi-stationary, more or less barotropic, and it's a dominant feature. It varies from daily, seasonal, as well as interannual timescales. The way to think about this physically is that it has 3 regions where you're getting a warmer wind from subtropics close to Antarctica, and 3 regions where you're taking this colder wind from Antarctica to subtropics. So in a way, it is important for the meridional heat and momentum transport between mid latitudes and high latitudes. Now, all right, so we know that SAM is really important. It has impacts throughout the Southern Hemisphere, but then why should we care about these zonal asymmetries when they present a really small fraction of the total variance? So as I said, they are important for meridional heat and momentum transport. And recently, this wave number 3 pattern got a lot of attention from scientific community after this 2015-2016 Antarctic sea ice decline episode. So what I have here is a sea ice extent going from 1979 up until 2016. And if you look at only the blue line, which is a September-October average, what happened was from 1979 to almost 2015, there was a slight increasing trend in Antarctic sea ice. A lot of people have been trying to understand why this is. And there are some theories, but in 2016, there was an unprecedented decline in Antarctic sea ice cover. We lost more than 30% of Antarctic sea ice in a matter of a couple of months. And this sudden decline was linked to a strong variability in the zonal wave number 3 pattern. This is from a paper by Guomin Wang et al. From Bureau. And so what this shows is how this zonal wave number 3 basically impacted this sea ice variability. So what I have here in the top panel, the shading shows meridional wind anomaly during September-October of 2016. The vectors show wind anomalies during that time. And the bottom panel shows the Antarctic sea ice anomaly during those 2 months. Now you can see that there is a clear wave number 3 pattern. There are 3 highs and 3 lows, 3 reds and 3 blues. And a similar wave number 3 pattern can also be seen in Antarctic sea ice. Now, if you look closely, the regions where you have the warmer wind, which is coming from subtropics to Antarctica, you see a melting of Antarctic sea ice. And the regions where you have colder wind going away from Antarctica, you see expansion of Antarctic sea ice. And this goes on throughout the Antarctic continent. Now, because these 3 nodes are not symmetric, the net result was a reduction in Antarctic sea ice. So we know that this pattern is important for not just for Antarctic sea ice, also for blocking events and a number of other things. But one thing which we don't clearly understand is why this pattern is actually present. There is a hypothesis that we have been believing, but we still do not really understand why this is actually there. So the hypothesis that we have, it was first presented in 1972 by Harry Van Loon and others. And they suggested that maybe this pattern is present because in Southern Hemisphere, we have this interesting land-ocean geometry. So we have got 3 land masses. We have got Australia, South America, and Africa, and 3 ocean basins between them. And they said, maybe because we have these 3 land masses, you get a wave number 3 type pattern. It kind of made sense because if you look at the climatological mean wave number 3, which I'm showing here, the 3 highs are always close to the land masses, and the 3 lows are in the ocean basins between them. So it kind of made sense. But no one really tested this in a climate model or understood why, if it's actually true. So we thought, all right, let's test this and this method, if this hypothesis is true. And before I go into the explanation of what we did, there are a couple of problems with this hypothesis. The first problem is that this pattern is not stationary. It's quasi-stationary. So it shows a seasonal variation in phase. It means that the highs and low pressure nodes, they do not stay at one place, they shift during different seasons. If this pattern was only created by land masses, we won't expect that shift to happen across different seasons. The second problem is that a similar pattern is also present in Northern Hemisphere, where this has been connected to extremes in extremes over the Northern Hemisphere extratropics. And in the Northern Hemisphere, we don't have this obvious 3 land, 3 ocean geometry. So for this reason, we started exploring this further to see if we can understand this pattern further. So for this purpose, we used NCAR CSM. NCAR CSM because it's known to simulate Southern Hemisphere climate really well. We use this in an AGCM setup. It means ocean and sea ice are just data models, they're not active. So the active models are CAM4, which is atmospheric component, and land model, which is kind of part of the atmospheric component itself. All the simulations that we do in a pre-industrial control setup. So we do not change any radiative forcing. So all the greenhouse gases, aerosols, ozone, everything is constant. And because we want to understand the mechanisms or the features which create this zonal wave number 3, we start with a really simple configuration. We start with an ecoplanet, where we do not have any land masses, any mountains on the Earth. It's full of water. And then we keep on adding bits and pieces of land and mountains to see what creates this pattern. So as I said, we start with ecoplanet. There are no land masses. The outline here is only shown for reference. So it's the planet full of water. And in the next simulation, what we do is we add a single landmass over South America. This is kind of an obvious choice. So the question that we have, the hypothesis that we have is that these 3 land masses are creating this pattern. So the obvious thing to do is let's just put 1 and see if it creates wave number 1. And there are no mountains in the second simulation. It's a flat land mass, basically at sea level. In ecoplanet, as we expect, we don't really see any wave number 3 because it's a completely zonally uniform system. So there is no zonal asymmetry which can create that pattern. But surprisingly, when we added a single landmass, we saw a wave number 3 pattern in both the hemispheres. This was kind of surprising because we didn't expect a single landmass to create a wave number 3 pattern in Southern Hemisphere. Then the reason also we chose South America instead of Africa and Australia is that South America has got an interesting meridional extent. It has a tropical part, and it also has an extratropical part which goes close to the westerly wind jet. So which will can help us understand which of these 2 parts is important. So to understand that, we slice this South American part into 2 different regions. So one is the tropical South America, which now extends to 10 north, so 10 south to 10 north in the tropics. The other one is the mid-latitude South America, which is south to 20 degrees south. Again, there are no mountains. It's still a flat piece of land at sea level. Now, what we found is that it's only the tropical part which is important to create this zonal wave number 3 pattern. The mid-latitude part does not really do much. So this experimental setup for now, it shows that the tropical part seems to be important to create this wave number 3 pattern in Southern Hemisphere. But then we thought, all right, let's test the mid-latitude simulation as well. So this simulation is what the theory says. We say that the 3 land masses in extratropics create this zonal wave number 3 pattern. So we put all the 3 land masses. We now also have mountains on top of these. So we have so basically in Southern Hemisphere, we only have Andes. There are no mountains, not very high mountains over Africa and Australia. So we have, basically we added all the orography that we have on all these 3 land masses. And what we still see is that they do not do much in creating a wave number 3 pattern, right? So we find that it's the tropical bit which is more important in creating this zonal wave number 3. And I'll explain how that happens now. So I'll explain it using this simulation, the ACEAS, the tropical South America part. And so what we do is, if you basically put a land mass in the tropics, which is full of water, what will happen is, because land will warm faster, land will warm more compared to the ocean, you will see a lot of convection over the land, which is shown by outgoing long wave radiation here. So you see low OLR values on the landmass, which shows deep convection in this region. And this deep convection then converts to a wave train. Let's see how that happens. So on the right side, I show vorticity at different levels. So if we just look at the panel C first, and then we'll go up. So panel C is at 850 hectopascals, which is close to 1.5 kilometers. So basically in the lower atmosphere, just above the planetary boundary layer. And the top, panel B is at 300 hectopascal, which is in the upper atmosphere. So at 850 hectopascal, what you see is that you see a gill-type response, the Matsino gill-type response to a heating in tropics. You see two anticyclones on either side of the landmass or the source region. But you do not see anything propagating to extratropics. The signal is only contained in the tropical region. But that is not the case in the upper atmosphere. In the upper atmosphere, what you see is you see a clear wave train, which is propagating poleward and eastward. So this high, low, high, this poleward wave train propagating poleward and eastward, hitting the poleward waveguide and then reflecting back as a weaker wave train. So this mechanism basically creates this zonal wave number 3 pattern in the Southern Hemisphere. Now to understand this, Martin created this animation, which I think will clear this thing up more. So you have a heat source, basically a landmass, which gives you low level convergence, which results in deep convection in tropics. And because of that deep convection, you see this Rossby wave train, which travels poleward and eastward because the westerly jet strengthens as you go poleward. So it goes poleward and eastward, and it hits the poleward waveguide and then reflects back as a weaker wave train. So what this shows is that if you have a tropical source, you can create a wave train. Basically, you can create waves in Southern Hemisphere extratropics in the mean circulation. But what this still doesn't answer is that why wave number 3? It could be wave number 1, it could be wave number 2, right? It could be any other wave number. Because what is happening here is that in simple terms, you have a source of energy in tropics, and you now need to dissipate that energy using Rossby waves. So when this wave train is traveling, you have all the wave numbers in this wave train. Then why do we see a dominance of wave number 3 in this 50 to 60 south band? Now to answer this, we look at the stationary wave number profile, so which is shown by this dashed line. So stationary wave number, in really simple terms, it means that this wave number will be favorable according to the wind profile in the upper atmosphere. So the wind profile in the upper atmosphere decides which wave number is going to be favorable at which latitude band. And if you look at the latitude band of 50 and 60 degrees south, wave number 3 is the preferred wave number at this latitude band. And that's why we see a lot of wave number 3 variability in this latitude band. All right, so this was the first variability. And the next variability is Amundsen Sea Low. Amundsen Sea Low is in one of the most dynamic regions of the South Pacific. It is represented by this plus sign here. Amundsen Sea Low has gotten a lot of attention in the past because this is one of the only regions around Antarctica where we are confident that atmospheric forcing has a strong role in in creating changes in Antarctic sea ice sheet melting, in surface heating over Antarctica and other things. Now for Amundsen Sea Low, again, I'm going to answer the same question, why this is present in the mean. Interestingly, for Amundsen Sea Low, we have a bunch of theories going back to 1989. And people have proposed different hypotheses of why this pattern is present. So the first theory was presented by Bynes and Frederick in 1989, where they actually made a scaled down model of Antarctica, a physical model of Antarctica, and they put that on a rotating table, put water in it, and so what circulation is created by that topography. And in their very simple setup, they came up with an answer that you see a clockwise circulation in the Ross Amundsen Sea sector when you rotate the table. But because the setup was so simple, that was the only thing they were able to test. Subsequently, in year 2000, Walsh et al., they came up with another simpler model. It was a numerical model, and they used that model to understand if this topography theory was right. So what they found was that topography does not seem to be that important. It's just the shape of the continent. So what they said was that even if you flatten Antarctica to sea level, it's just the shape of the continent which creates this low pressure in the Amundsen-Ross Sea sector. And then more recently, Ryan Vogt and others, they came up with a theory that maybe it's the cyclonic activity from the extratropics which end up in this region. And the reason why their theory made sense is that we see a lot more cyclones during winter, which end up in this Ross and Amundsen Sea region compared to summer. And Amundsen Sea Low is deeper in winter compared to summer. And that is how kind of they connected this, the seasonality of Amundsen Sea Low with cyclones. And they said maybe it's just a cyclone which is creating this low pressure. And then quite recently, a couple of papers suggested that maybe it's a tropical convection, similar to what I showed for wave number 3. They said maybe it's just a tropical convection which is giving you this low pressure in the Amundsen Sea sector. And the reason for this theory is that we know that ASL responds really, really well to ENSO. So during the positive phase of ENSO during El Nino, we see a shallower ASL. And during the negative phase, during La Nina, we see a deeper ASL. It's really a well-established theory, and they suggested that maybe the mean is also created by this tropical convection. So again, we did the same thing. We took the same model and cast CSM, and we thought, all right, let's test all these theories and see if we can come up with a single answer. So these are the bunch of experiments that we carried out. So panel A just shows the topography over Antarctica, what it looks like. So East Antarctica has most mountains, topography goes above 4,000 meters. West Antarctica has very few mountains. And in panel B, I'm just showing the control simulation. So this is MSLP, the mean sea level pressure in the control simulation. So control is just pre-industrial control. There is no change in forcing. I have removed the zonal mean to highlight Amundsen Sea Low. So the plus sign shows the ASL location. Now what you see is that the model captures ASL in the location where we see it, in the Ross and Amundsen Sea sector. In the next simulation, what we do is we remove topography. So we removed mountains from around the globe. So we still have land, but everything is at sea level. When we do that, what you see is that the ASL is gone. We instead have a high pressure in the Ross Amundsen Sea sector. So the first observation was that, all right, topography seems to be important in creating this pattern. Now, then the next simulation, what we did is the obvious one, we added topography only over Antarctica. So everywhere else, it's still flat. The topography is only added over Antarctica, shown by these contours. And you see that panel B and panel D are more or less the same. So it looks like it's just the Antarctic topography which is creating this pattern. Now, there is still one more question. So ASL is really constrained in that region. It does not move like past this peninsula. Now, we don't know if this is just the mechanical effect of these mountains in the West Antarctic region, or this has to do with something, this has something to do with the thermodynamics or dynamics which are occurring because of other reasons. So to do that, we flattened the mountains in the West Antarctic region in this simulation E. So we still have mountains in the East Antarctic sector, but we have no mountains in the West Antarctic sector. And we see that the ASL shifts westward and is now close to Antarctic Peninsula. So which tells that it's just a mechanical forcing or just a mechanical barrier given by the West Antarctic mountains which constrain or trap this low pressure in that region. Now, all the simulations point to the role played by the Antarctic topography, but one thing we still can't rule out from A to E is the role of tropical forcing. Because in C, we can say that, like, we still have tropical forcing when we remove topography. But the problem here is that the moment you remove topography, you change the tropical teleconnection as well. The waves can now go all the way. You do not have any mechanical barrier for the waves to stop at that location. So to overcome that, Martin came up with this interesting idea, and we took this up. So we rotated Antarctica. So if you look at this, South America and New Zealand, they are still in the same location, but Antarctica is rotated eastward by 100 degrees. So the peninsula is basically now close to New Zealand. And it's really fascinating that the ASL, basically it revolves with Antarctica. So it's just a purely mechanical effect of interaction of westerly wind jet with the orography of Antarctica, which creates this pattern. So you can think of this like an aircraft wing. So when the flow goes over an aircraft wing, at the edge of the aircraft wing where there is no surface, you see these eddies forming because you have a wake region. There is no surface there. That is exactly what is happening in the Ross Sea sector. The only difference here is that in the aircraft, that wake goes like to 1 or 2 kilometers. Here you have mountains, which is basically trapping that low pressure in that region. So we are still not completely convinced. We thought like, all right, if this is so simple, then we do not really need a climate model to show this. This should be clearly seen in a barotropic, non-rotating simulation, a really, really simple model. So that's kind of what we did. So we used a model called ANSYS Fluent. It is used for aircraft design when they design aircraft wings and they test these in wind tunnels. So we used that software and we carved out shape like Antarctica in Mercator projection. So this is what it looks like. The only assumption is that the topography is same at each location. So it's a 3D shape. The topography is same at each location. And then we virtually put this in a wind tunnel, basically a westerly flow around it. And this is what this looks like. So you see that when the wind flow reaches this Victoria Land region, this high orography of East Antarctica, it separates from the surface because there is a wake region after that. And it creates this clockwise circulation, which is constrained by, in this region by the West Antarctic mountains. So this kind of suggested that it's just purely an aerodynamical or mechanical effect of the mountains interacting with the westerly wind jet, which creates this Amundsen Sea Low circulation. All right, so this was about the mean features. So we had 3 mean features. SAM, I touched a little bit, but then wave number 3 and Amundsen Sea Low. The next thing is how do we measure variability in these features? So for SAM, we know that there are 2 simple ways to do this. One is just the difference between MSLP, between mid latitudes and high latitudes, basically a zonal mean of MSLP between these 2 latitude bands. Or in the other method is just looking at the leading EOF of SLP or geopotential height in the extratropics. The next one is zonal wave number 3. So we do have a couple of methods already which have tried to understand the variability in zonal wave number 3, but these methods are again based on this same assumption that the 3 land masses are creating this pattern. So the index that we have right now, the one which is most commonly used, was made by Meridional in 2004, and that index is just the average of normalized geopotential height in these 3 boxes. The assumption here again is that the phase of wave number 3 is more or less fixed. It does not shift much. So that is the major limitation as well. And now when we show that wave number 3 is not created by land masses, so any change in the location of tropical forcing will give you a change in the phase of the wave, which means that these high and low pressure nodes can basically move anywhere around the planet. So for that reason, we are now suggesting a new method of understanding the variability in zonal wave number 3. Another limitation with the method that we have right now is that these 3 boxes are decided based on reanalysis data. But we don't know if models also show these high nodes, high pressure nodes in the same region. So to look at this, we looked at a bunch of SIMP6 models. I think I've used 31 models and a couple of reanalysis products here. On the y-axis, I have the amplitude of wave number 3, and on the x-axis, I have the phase of wave number 3. Now what you see, let's just only focus on the x-axis for now. In the x-axis, you see that models show a huge range of bias in the phase of wave number 3, which means that these boxes will not align with the high pressure nodes for all the models. Sorry about that. Okay, it's gone. So it means that the models show a huge bias in the phase of zonal wave number 3, which means that these boxes may not align with the high pressure nodes for different models. So either we have to use different boxes for each model. So this method cannot directly be used for climate models. The other problem is this. So it's the same figure as before. I've just added these dashed horizontal and vertical bars. What these bars show is the interannual variability in the phase and amplitude of wave number 3. Again, let's just focus on the horizontal bars for now. What you see is that there's a lot of interannual variability in the phase as well. So at some point during 1 year, the wave number 3 phase doesn't have to be exactly in that same location. So the phase varies quite freely. And this has also been suggested by a paper by James Renwick, where he says that wave number 3 has a huge range of variability in the phase. So to overcome that limitation of fixed phase in the wave 3 index calculation, we came up with this new method using EOFs of meridional wind anomalies. So what we have done is we have taken the middle atmosphere meridional wind anomalies, and I'm showing you the first 3 EOFs. Now the first EOF clearly looks like a wave number 3 pattern. The second EOF is also a wave number 3 pattern, and the third EOF looks like wave number 4. So this means that we need to use a combination of the first 2 EOFs to create a new index for wave number 3. And if you look closely, EOF1 and EOF2 looks like they are in quadrature. So our index is a 2-part index. The first is zonal wave number 3 magnitude, which is simply square root of PC1 square plus PC2 square. And the second one is the zonal wave number 3 phase, which is arctan PC2 by PC1. So by doing this, the phase one especially, what we can do is we can create any phase based on the combination of EOF1 and EOF2. I'll show you an example of how this is useful. So when we look at the phase, right? So wave number 3 is basically 3 regions of warm wind and 3 regions of cold wind. And if we do not know which those regions are, we won't be able to understand where we see the sea ice variability or similar regional variabilities. So to show this, what we did was we made a scatter between PC1 and PC2. Let's just first focus on the scatter in the center. So it shows the scatter between PC1 and PC2. So you can see that it's all around the place, which means it can show any phase. It's in all the quadrants. Now, I also have a circle in the center, which shows 50th percentile. And the reason why this is a circle, because by definition, our magnitude index is PC1 square plus PC2 square, which is an equation of a circle. So this circle represents 50th percentile, and the dots outside that circle are those events which are stronger than the 50th percentile. The next thing which I do is I do composites of wave number 3 events in different phases. So I've chosen different sectors, each of 20 degrees in width from A to H. So in the shading, the outer panels, the shading shows composite of Antarctic sea ice concentration anomaly in different phases, in different, basically these sectors. And the contours, they show meridional wind composites in this each sector. Now, what you see here is that if you just follow from A to H, if you just follow these arrows, what you see is that the anomalies also rotate clockwise. So even if you just take one example, let's say this positive anomaly keeps on rotating clockwise as you go in different sectors of the phase. So this shows that if you want to understand the regional variability in Antarctic sea ice, the information about phase is really important. And that's, I think, one of the advantages in using this index. So the next is the ASL index. ASL index, it has been used we are using it from maybe last 30, 40 years. So it's simply the lowest MSLP in this sector here. And I'm not going too much into that. All right, so this was how to understand the variability in these features. Now I'll be brief here, but I'll talk about historical and future changes that we have seen in the circulation in Southern Hemisphere. So this is a change in SAM index. This is from a bunch of SWIP 5 and SWIP 6 models. And I've also put future projections in. And I have the moderate emission scenarios, which are shown in blue, and the high emission scenarios, which are shown in red and orange. I also have ERA 5 data, which is reanalysis from 1979 to 2019, I think, in this figure. What we see is that in the last few decades, we have seen a positive trend in SAM, which has resulted in an intensification of the westerly wind jet and also a poleward shift in the westerly wind jet. And we expect that shift to continue further in the future. If you look at the high emission scenario, it continues till the end of the century. If you look at the moderate emission scenario, it stabilizes somewhere around 2050. Now, if you look at the contributions that we have to the SAM trend that I just showed, there are two major factors. There is stratospheric ozone and there is greenhouse gases. There is some contribution from aerosols, but it's not as strong as these two. So in the last 30 years, more or less, we have seen a strong decline in Antarctic in stratospheric ozone over Antarctica, and that has given a positive trend to SAM. We have also seen increase in greenhouse gases, which have also given a positive trend to SAM. In the future, we expect the Antarctic, the stratospheric ozone to recover. We are already seeing signs of recovery, and we expect the recovery to happen somewhere between 2060 and 2070. The estimates are all over the place, but somewhere around that. And greenhouse gases, we expect that they will increase, but I hope that's not true. And so if you look at their contribution to SAM, this is from a paper by Dave Thompson in 2011. The panel A shows the contribution of SAM from just ozone depleting substances, just from ozone, and panel B shows the contribution from greenhouse gases. If you look before 2010, ozone was the dominant forcing which was driving this trend. Greenhouse gases were playing a minor role. If you look at the future, ozone contribution is decreasing because we expect the ozone to recover. So basically, ozone is giving a negative contribution. Greenhouse gases are going to give a positive contribution depending on which scenario we follow for the future. So in other words, in the past, ozone and greenhouse gases, they both were helping each other in giving you a positive SAM trend. In the future, ozone is basically compensating for some of the increase in trend that we see from greenhouse gases. Now, if you look at a similar thing, if you look at the change in the westerly wind jet, similar to the change in SAM, positive trend in SAM simply means a poleward shift in the westerly wind jet and a strengthening of the westerly wind jet. That is exactly what we have seen in the past. The top panel shows the location of the jet, which has shifted poleward in the last few decades. And the bottom panel shows the strength of the jet, which had strengthened in the past few decades. In the future, again, it either shifts poleward or it settles at one latitude, depending on the scenario that we take. Now, one thing which I would like to point out here is that if you look at the top plot, the location plot, CMIP 5, the mean location of jet in CMIP 5 was around 50 degrees south. Whereas if you look at ERA 5, the mean location was around 52 degrees south. So there was close to 2.5 degrees difference in the mean location of the jet between CMIP 5 and ERA 5. Because of this strong equatorward bias, this was a problem for oceanographers when forcing the models with projected changes in the westerly winds. So what oceanographers generally do is they take the mean, basically the mean state from reanalysis, and then they take the future anomaly fields from CMIP models, and they add that anomaly field onto this, the mean fields from the reanalysis products. But with CMIP 6, we have gotten rid of most of this equatorward bias. So it will be much easier to run CMIP 6 models, to the ocean models directly with CMIP 6 forcing. Okay, and before I move to the next slide, I just want to mention one thing. This is how we are used to seeing the changes in the westerly wind jet. We always look at the zonal mean change, and we show that the westerly wind jet is shifting poleward, it's strengthening. But is that change zonally symmetric, or are there zonal regional variations in that change? This is what that change looks like in the end of century. So you see that yes, the most of it is zonally symmetric, but there are regional variations in that change. And now we know that these regional variations can be important for Antarctic sea ice as well as for atmosphere in terms of blocking events and other things. But are these changes important for oceanography, for ocean circulation and warming that we see in the future ocean projections? If I take the mean of this is what it looks like. This is south of 20 degrees south. And this is generally the forcing that we apply in the ocean models. So we take the mean state from reanalysis, or the present state from reanalysis, and then we add a zonally uniform anomaly to that present day forcing. This is what the difference in that forcing looks like, and it is consistent across different CF6 models. So the difference, it is half the magnitude. The color bar is half now. It is half the magnitude of this, but it is still present. So the next thing we thought, like, let's see if this is important for ocean circulation. So we went to an ocean model and we tested this. So for this purpose, we used the Australian model to access OM2 at 1 degree resolution. It's an ocean sea ice model, which is forced with prescribed atmospheric forcing. And the atmospheric forcing fields we take from the coupled atmospheric model, access CM2, and we carry out different simulations. I won't go into the details of simulations, but what we do is we separate out the effects of symmetric and asymmetric parts. If you look at the SST sea surface temperature response, this is the total change at the end of century. So the total SST change at end of century, this is what we are used to seeing. So we see a lot of warming in the western boundary current regions, a lot of warming in the ESC region, a lot of warming in the Atlantic, and muted warming in the Agulhas. If you look at the symmetric case, which is explained by only the symmetric anomaly, zonally uniform anomaly, it captures most of this change. So as you can see, it captures most of it. But if you look at Amundsen Sea and Southern Australia region, the warming is now muted, and that difference can be explained by the asymmetric part that you see here in panel C. Then we thought, like, let's see if this is connected to changes in ocean circulation, or if this is just a change in the heat fluxes that we are forcing somehow. So then we looked at the upper ocean circulation. So here I'm showing the depth integrated velocity in the upper 100 meters of the ocean. So top two panels are just for reference to show how the circulation looks like. If you just follow the left column, panel A shows the East Australian current, which flows eastward and then reflects, which flows poleward, southward, and then reflects eastward as Tasman front. In the future, panel C, we expect the extension of that region to intensify and the Tasman front to weaken, which is a well-known feature. And again, symmetric part in panel E gets most of it, but then asymmetric part also has a substantial proportion of that change is also explained by asymmetric change. We also see some changes in the Indian Ocean, in the Agulhas current region, but the changes are quite muted. What this means is that if we force our ocean models with the zonally symmetric anomaly, we'll be underestimating some of the changes that we see, especially in the Pacific region. So this brings me to the end of the presentation. This is something that I'm doing now. So as I said, we have looked a lot at the tropical teleconnections to Amundsen Sea Low and how atmospheric forcing in this Amundsen Sea sector influences Antarctic sea ice sheets as well as the surface temperature. But we hardly know anything about East Antarctic sector, that the role of atmospheric forcing in the East Antarctic sector. So this is something that I'm working on right now. And it looks like wave number 3 has some sort of signature in influencing surface temperatures over this region, but we're still in the early stages, and this is what I'm working on right now. If anyone is interested, please feel free to reach out. So just to summarize, so wave number 3 I showed it's created by tropical convection, and extratropics do not really do much. Surface provides a perturbation, and upper atmosphere controls a teleconnection and decides that it has to be wave number 3, which is going to be dominant. For Amundsen Sea Low, we showed that topography is important, and the other theories that have been proposed do not seem to be true. And I also showed that the future changes in the westerly wind jet they also show strong zonal asymmetries, and those asymmetries are also important for ocean circulation in certain western boundary current regions. Thank you so much.
Fantastic. Thanks, Rishav. There was a lot in there. So we have a few questions in the chat to start with.
Adele, you're muted, I think.
You know,
I can hear you.
We can hear.
Oh, you can hear me now? Okay. Right, so there's a few questions in the chat. So perhaps if we start with those, and then if anyone else wants to ask a question, if you could put your hand up. So yeah, Jan, go for it.
Oh no, I was just making the observation.
Voice is, I can't hear you.
Rishav can't hear us. Okay.
Can.
You can now?
Yeah, I can now.
Okay.
Okay.
Good, yeah.
Did you want to ask that, Jan? Or?
Oh no, I was just
Yeah.
wondering if you'll go right back to where you did an aquaplanet run. And there's a really faintly, maybe it's just some sort of artifact. There's really a faint there's a really faint wave number 3 pattern.
Yeah.
And I just was commenting on that figure, just whether there's something innate even about a aquaplanet that wants to give you a wave number 3.
Oh, yeah,
it's
something
just
here, right?
coincidence. Just before that, yeah, that's far left. Yeah, I mean, maybe you could have got rid of it by choosing to not put 0 as one of your thresholds.
Yeah, that is true. But that is true. But the thing is, there is a faint wave number 3.
Yeah,
and
right.
for that is probably the radiation time step that's used in the model. So what's happened, even in an aquaplanet, if the sun hits the same spot at the same time, like after every 6 hours or so, you will create a zonal asymmetry in that. So we think it's really, really faint, but there is still a hint of a wave number 3. So yeah, that is, I think, the
okay. So if you changed it to a 4-hour time step, you might get a different wave number that is wave number.
Yeah, true. I didn't change the radiation time step. It's really weak.
Interesting. Okay. Thanks.
Okay, Timur, did you want to jump in and ask your question?
Yeah, thanks, Adele. It's a really silly question, I think, but with the ANSYS fluent simulations, when I've used it in the past, I mean, I used it for wings. So I used it in the order of 0 to 10, 1 to 10 meters kind of spatial scales. I was just wondering, did you get the spatial scales correct in the simulation you had there, of order like, thousands of kilometers, or?
Yeah, no, that's right. So I got spatial scales exactly right. The only thing I did is the mesh is really coarse. So the problem with ANSYS is you can't have a really fine mesh if you go with a higher scale. So the scales are correct, but the mesh is like really coarse, which is okay, I think.
Yeah, sure. And the other question I had was just about your zonal wave 3 index calculation. The EOFs that you got, was that across all the models, or did you just look at a single model and get the first 2 from that and then applied it to all of them? How did that work?
Yeah, so the one I showed is from reanalysis from ERA 5, but I also tested this for a bunch of different models. So it shows it for different models. I can just show you that.
And so for all those models, the first 2 were the only relevant EOFs for the zonal wave 3 pattern?
Yeah, I'm sorry, your voice is picking up. I don't know, it's some issue with my side. I hear a few things, I don't hear a lot of things. Okay, might be somewhere here. Yeah, here it is. So I do the same calculation for a bunch of SIM6 models. I think I have 24 models here. And we get the same pattern in most of the models. So I think 22 models showed the first mode as wave 3, and 19 showed the second mode as wave 3.
Okay, cool. Thanks.
Okay, and then I think Paul Spence, you had a question in the chat. Do you want to ask that?
Yeah, thanks. Great talk, Rishav. Thank you. It's awesome work. Do you have any idea what happened in CMIP 6? They fixed the position bias in the westerly winds? Do they know, or it just like happened, or what did they do?
Yeah, I'm not too sure, but I just recently read a paper where they said they fixed something in the clouds. So there was a shortwave cloud bias in the CMIP 5 models, and they say that that bias has been reduced now.
Cool. It's always the clouds. Thanks.
Can I just ask a follow on from that? So is the change that you see in CMIP 6 similar to the change in CMIP 5?
Now the change is smaller.
Okay.
So in CMIP 5, the change was dependent on if the models are showing a larger bias. So the models with larger bias showed more change in the future. So the change in CMIP 6 is smaller than change in CMIP 5.
Okay, it still looked fairly substantial, the change though, I think that you showed.
So the change it's substantial, I think.
Yeah, it didn't look that much smaller, I think, from the plot.
Here. If you go to different seasons, you see that the change is quite significant in some seasons.
Okay. Would anyone else like to ask a question?
Rishav, could I ask a question, please? That's
Yes,
Mike Ebry speaking. Hi, thanks for the talk. It was great, as usual. You showed the South American 10 North, 10 South landmass experiment. Did you get the same effect if you put 10 North, 10 South on at over Africa or over the maritime continent?
Yeah, so we did that. You get the same effect. The only thing is that the magnitude will be different. The magnitude is different, and the phase is different.
Right. So the next thing is, I might be very confused here, but with waves, they interact and reinforce or affect each other. So if you've got sources from 3 tropical sources, how are those 3 causing the final effect that we get?
Yeah, no, that's a really good question, and I should have clarified this. So when you look at the real system, we actually have one of those simulations. In the real system, the strongest source of convection is the Indo-Pacific worm pool. Land masses contribute really little to the actual wave that you get. So we did another simulation in which we had the whole tropics. So we had all the 3 land masses, and we have that real SSTs in the tropics. So what you see is that most of that change comes from the Indo-Pacific worm pool. So the message is that you only need a source of known uniformity in the tropics to create that change. But you're right, if you have multiple sources, like we saw in 2016, you will have a completely different effect, and you cannot simply apply a linear theory and get the phase and magnitude right.
Great, thank you.
Answer your question?
Yeah. So, another question is, your illustration showed a baroclinic sort of effect with the Gill-Matsuno response at the tropics, but it was a barotropic wave at the high latitudes. How does that come about?
So my understanding there is that if you will see a Gill type response if you have any source in the tropics, right? The Gill type response is only in the lower troposphere. In the upper troposphere, what you basically do is, if you have a source in the tropics, you basically create a local Hadley cell, which will take that signal from the tropics to subtropics. I should actually go back to that figure and it will make it more clear. I tried to not go too much into the dynamics for some reason. I should have. Okay, yeah. So if you see the panel B here, in the upper troposphere, you see the wave train travels from the southern flank of the landmass. It does not travel from the landmass itself or where the landmass is. That is because the Gill type response is only giving you deep convection and a perturbation that can take the signal up. And what happens after that is you form a local Hadley cell, which takes the signal from here to subtropics, where you get the westerly winds. And that westerly winds then take the signal and propagate it basically advect it to the higher latitudes.
Right.
Does that make sense?
Yeah, I was just connecting that with something you said right at the beginning, which was that the zonal wave 3 signal at the was a barotropic signal, but this figure looks like a baroclinic sort of response. I might be confused there.
Yeah, I'm not too sure about that. I still think that you will still see a barotropic type response. Even if your surface response is baroclinic, the upper troposphere doesn't have to be a baroclinic response. That's my understanding.
Okay, thank you. Thanks very much.
Okay, we have time for a last question or two. Does anyone have another question? Do your last one. So when you applied your future projection symmetric and asymmetric forcing, you found there was a strong cooling in the Southeast Pacific. Is that right?
Yeah.
Maybe you could just jump to that and we can see. Was that, I guess that's a region where there's, is that the same region where there's mode water formation? Does it, I guess I was wondering if it affects that or interacts with the mode water formation region there.
Yep.
Yes, so that cooling that you're seeing off South America on the right figure there.
Yeah, so this is just from surface heat fluxes. So in the surface air temperature anomaly, you have this cooling in the South Pacific, and because when you apply the zonal asymmetric, you get rid of this cooling. So this is just the surface heat fluxes giving that strong cooling. It doesn't have to do anything with the dynamics. So we looked at the circulation change, and there is no change in the circulation there.
Okay, right. Thanks. Okay, so perhaps we'll leave it there. So yeah, very impressive set of studies you've done, Rishav. So let's thank Rishav. And we'll see.
My speaker. I think I still missed a lot of comments and a lot of questions, probably a part of it at least.
Sorry. Yeah, thanks very much, Rishav. Yeah, we'll catch you all next month. See you.
Thanks.
Thank you.